So we want to make another episode of the Super Science Power Hour, right?
Mm-hmm.
But we've covered, what have we covered? We've covered
Impulse.
We've covered impulse and momentum and what's the other one?
Thermodynamics.
Thermodynamics. We covered thermodynamics.
That's true.
So what else can we do it on? Let's think on this.
Kinetic energy and potential energy. That's a pretty good one.
Yeah, we can do that.
Electricity and magnetism, that's a pretty good idea.
Yeah, that's
Guys, I got it! Back-to-back episodes!
Yeah!
Yeah, let's do it! Kinetic and potential energy.
Today we have the opportunity to witness a historic matchup of ping pong between Forrest and Gum. And in the process we'll also get to learn about kinetic and potential energy. Point for Gump!
Okay, so let's start with the basics. So kinetic energy is the energy of an object resulting from its motion. So this occurs any time the ping pong ball is moving, and the maximum would be when it hits the table because it has the most energy. The potential energy is the stored energy of an object resulting from the gravitational force between Earth and the object. So the maximum potential energy occurs when the ball is at its peak and it is farthest from the table because it has the maximum potential to increase in velocity before hitting the table.
The conservation of mechanical energy shows the relationship between kinetic and potential energy before and after a reaction. Before the reaction, kinetic and potential energy must equal the sum of kinetic and potential energy after the reaction. Kinetic energy, the equation for kinetic energy is 1/2 mass times velocity squared. Potential energy is mass times the gravitational acceleration times the height of the object.
Alright, so here we have an illustration of what happens with the kinetic and potential energy as we're throwing the ping pong ball. So you start off, when you hit it and it reaches its maximum height, you have a maximum potential energy. And then as it's falling, the potential energy decreases and the kinetic energy increases until a point about halfway where they are equal. And then when you get to the bottom, a point just before it touches the ping pong table, you have a maximum kinetic energy and 0 potential energy. And then it bounces and the kinetic energy starts decreasing and its potential energy increases till they're equal again, and then finally you reach at the maximum height another maximum potential energy and start the process over again.
Potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic. Slam it!
I tore my ACL!
So did the ambulance.
Hold on, wait. We gotta put this on YouTube.
Jerks!
Electricity and magnetism.
The first concept we'll be illustrating is the right-hand rule. So there's 3 of these. The first one is a method you can use to determine the direction of a magnetic field relative to the direction of a conventional current. So we have here a circuit. This is the positive terminal, so the current is going to be flowing in this direction. Now if I place my thumb so that it's going in the direction of the current and wrap my fingers around the wire, this is the direction that the magnetic field will be going. The second right-hand rule is a method you can use to determine the direction of the field produced by an electromagnet relative to the flow of a positive current.
So here we have an electromagnet, and so the positive current is running this direction. So if we wrap our fingers around the magnet, our thumb will point to the north direction of the magnet. So when we turn it on, the compass flips around, so this is now north, which makes the compass south attract, and if we add more power, the magnet will flip around as well and attract.
The third right-hand rule is a method used to find the direction of the force on a current-carrying wire in a magnetic field. So we have 2 magnets here. This is the north end of this magnet and the south end of this electromagnet. And the current in this wire is going to go from the positive terminal to the negative terminal, so in that direction. We're going to start by placing our fingers in the direction of the magnetic field created by these 2 magnets. Then we're going to point our thumb in the direction that the current is going in the wire, so like that. The force on the current carrying wire is going to be coming directly out of my palm. Watch what happens when we turn on the current in the wire. Off, on.
This is a Van de Graaff generator, and we will use it to show you how mechanical energy is transferred into electrical energy. So I'm going to remove the dome, show you what's inside. So how it works is, the mechanical energy built up by the moving belt creates a potential mechanical energy right here, and it is collected by the comb, this metal comb right here. This potential energy is distributed around the dome, and the dome itself acts as a capacitor, which charges the current long enough until it creates an electric spark, which we will show you right now.
Good.
Here's a demonstration on how this works.
For the best effect, we'll turn off the lights.
Right now it is being charged, the dome is charging up a current like a capacitor, as I said, and when I bring this metal dome closer to the thing, you'll see an electric spark jump out. The mechanical energy built up by the belt is being transferred to electrical energy, which is being built up in the dome. So watch. Shocking, isn't it? So Brandon, tell me about magnetic fields.
Not only will I tell you about magnetic fields, I will show you. See, when you put a current through this coil of wire, it creates a magnetic current. Compared to something like this where there's already a core of metal, this one is hollow. So, let's say that you turn this on. When you put this inside this hole right here, it will levitate. This is like magic, but real.
Amazing.
So in conclusion, we learned 3 right-hand rules. The first rule is where you wrap your fingers around like this. If there's a wire and there's current running through it this way, a magnetic field will go around the way that your fingers are. The second right-hand rule is where you have this same shape, except instead there's a coil of wire, and in this case the magnetic field will go this way, where your thumb's pointing. The final right-hand rule looks like this, where if you have a current running this way, you'll have the magnetic field pointing where your fingers are, and the force is pointing upward.
Alright, so here with the Van de Graaff generator, we learned mechanical to electrical energy and created a spark.
In the last example, we saw how when you put a current through a coil of wires, a magnetic field is created. And we showed that by taking a piece of metal and putting it through the hollow center, and it levitated. It did not move because the magnetic field kept it in place. Stop.
Boys.
Okay, so you put the wire in here, right?
Yeah, so you attach the wire right here,
Oh, okay.
and you start the power,
Uh-huh.
and it starts spinning.
Hey, that's cool. Hey, what does this do? No!